ensemble theory okay ensemble theory indicates the fundamental statistical mechanics or classical mechanics. We know that when in thermodynamics there is a close relationship between entropy and various states. Here we explain macro state and micro state, the phase space and phase trajectory of the system. We know the energy, volume, and the pressure, temperature. These parameters or thermodynamic variables are well defined and they are considered as universal. So the number of particles, volume, plays in statistical physics require certain description of the system, and the microstates or the configurations corresponding to particular arrangements either in classical mechanics or quantum mechanics are able to describe the individual states. Yesterday we have discussed phase space. Phase space is a 6n dimensional state. We have a single particle. If we consider in one dimension, it has time t and position vector is xt. Corresponding momentum is p. So the microstate have 3n dimensional position coordinates and 3n momentum coordinates. Altogether, it becomes 6n coordinates. Now, you can say how we can recall the different ways in which the particles can be expressed in phase space. Phase space is of two types. One is mu space, another one is gamma space. If phase space is generated by generalized coordinates and conjugate momentum coordinates of a single particle, then the microstate given at any instant of time t is described by n points. These are the n points. This is your pi, that is momentum coordinate system, and this one is your coordinate system, generalized coordinate system qi. If we have n number of particles, then we can represent this in n state, and if it is gamma space, then we can represent this in a single point. Here the Hamiltonian equation of motion, that in classical mechanics we have the q1 dot t, that is generalized component, time derivative, the time evolution of microstate, that is q is a function of t and p is a function of t of the system, is governed by this Hamiltonian equation. That is q1 dot t is del h by del pi and p1 dot t is minus del h by del t. So in a microstate, if you have mu space and if you have gamma space, in mu space you have represented this by large number of points in the phase space diagram. In gamma space, all these are represented in this a single point. There are, though it is 3n dimensional space, they are represented as the microstate, and it is representation of 3n generalized coordinates. So a single point is capable to represent 6n dimensional space. Now, the corresponding velocity, we can represent the trajectory through this equation, that is v is q1 dot into q1 cap. Velocity is a vector, that's why q2 second particle q2 dot q2 cap, and so on q3n, because it is coordinate, there are 3n coordinate systems, q3n q3n cap. Then this one will be p1 dot p1 cap, p2 dot p2 cap, dot 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 p3n. These are momentum coordinates, these are generalized coordinates. So if a system is isolated, well, the Hamiltonian does not depend explicitly on time. We know. In classical mechanics, we know the phase space trajectory will be limited to certain hypersurface in gamma space. That means the Hamiltonian, which is a function of QP, represents the total energy of the system. Suppose the Hamiltonian, which is a function of QP, varies between energy E and E plus delta E in a phase space trajectory. Then the trajectory will be limited in the hyperspace. We can see this picture, that this is a representation P, which is a function of T, Q, which is a function of T, then the phase space trajectory is like this. This represents a constant energy surface. This one is a constant energy surface, and this one is the energy varies here from E, this is E, and this is E plus delta E. Here the energy is E. Now we can represent the phase space trajectory in this manner. One is for constant energy and one is between a phase trajectory space with variation of energy delta E. Now the question is, what is difference between time average and ensemble average? Time average and ensemble average, these two equations, I will tell that time average is given by F bar. F bar is limit t tends to 0, 1 by total time t, ranges from t0 to t0 plus t, of a function f, which is a function of coordinate and momenta qt and pt into dt. So what do you mean by time average and ensemble average? We first concentrate on time average of a function f is given by f bar, that is 1 by t times sum over I, if we have I number of cells, fi delta ti. But if we change the summation to integration, by summation we can represent fi bar is 1 by t sum over I fi delta ti. But here the f is a function of qi and pi. Qi is a function of t, pi is a function of t. That means both coordinates q, which is a function of t, p is a function of t, can be written as q1t plus q2t and so on. In this manner, we can represent the time average of a function is the limit t tends to infinity 1 by t, and the time varies from t0 to t0 plus t dt f of qt into pt. If you consider the ensemble average is represented by, which is by an ergodic hypothesis, it is represented by the expectation function. That means if we consider f as a parameter, then it can be represented in phase space, and f of expectation value of f is represented in phase space, then we say it is our ensemble average. So in order to represent that, we must know what is phase space density. So what is phase space density? Phase space density represents by rho ps or rho dash ps. Here rho dash ps represents this space density function, and it can be defined as rho dash rho s d omega, which is sum over continuous product in the small phase space volume element dqi dp, which is called to 3n parameters d3 and q, d3 and p, which is dq1 dq2 up to dq3n into dp1 dp2 dp3n. So the integration over the entire phase space, gamma space, this represent the ensemble average. That is rho dash ps. This means the phase space density function, which is a function of generalized coordinate q, momentum p, and time t over the small space volume d omega, which is equal to m. So let us use rho ps is equal to rho dash ps divided by m. So in that case, we define the normalized phase space density, and the phase space volume can be represented as integration over gamma space rho ps qpt d omega is equal to 1. So if we associate a fundamental volume in phase space, then we can find the rho qpt can be normalized to 1, where this is written as the above equation integration rho ps qpt d omega is 1. This represent a single individual microstate. Then a normalized dimensionless probability density function or a dimensionless phase space density function looks like this, that is 1 by omega 0 integration over gamma space rho qpt d omega is 1. Here omega 0 corresponds to phase space volume and microstate. So phase space density function should be visualized as probability density function. Remember, here you have written f bar is equal to 1 by t, that is your time average. But the ensemble average is expectation of f is 1 by omega 0 integration over gamma space d omega by f of qp rho qpt. So this represents the d omega fqp rho of qpt. This is ensemble average. The difference is, we have told you this is your time average factor, and this one is your time average is given here. Time average t f is written here, f bar is 1 by t fi delta t. This is time average, that is represents for your discrete integrals. If we take a summation, we get time average f bar 1 by t integration t0 to t0 plus t dt f, that is f is a function of this one. But the ensemble average, when we consider, the ensemble average represents your expectation of f is equal to, this is represented by means of density function 1 by omega 0. Integration is over gamma space. Their integration is from t0 to t0 plus delta t. This is d omega f of qp, and this is the density function, phase space density function rho, which is a function of qpt. So the phase space density function can be regarded as a weighting function of the ensemble, and fqp may be different for different systems. Further, the system exists in a pure state. Now we can say the ensemble average of any physical quantity fqp using the phase space density, we can obtain their normalization condition. What is normalization condition? We can write by this equation the same thing, the average of ensemble, this is ensemble average, this is time average. Here we can compare time average of a function f bar is limit t tends to infinity 1 by t integration t0 to t0 plus t dt f of qp, and ensemble average is 1 by omega 0 integration over gamma space d omega f of qp rho qpt. Mind the difference. This is f bar, this is f expectation. In time average we have f bar, in ensemble average we have f expectation. Here the integration is over t0 to t0 plus t. Here integration is from gamma space. Here this is 1 by t, this is 1 by omega 0. And the integration is the function of qp into dt. Here function of qp, in place of dt, we have replaced d omega into qpt. So for an ensemble, which is a static ensemble or stationary ensemble, that is del rho qpt by dt is equal to 0. If it is stationary ensemble, then this is del rho qpt by dt is 0. Therefore, when a system is in equilibrium, we say for stationary ensemble, the f expectation is independent of time and which represent equilibrium of a system. Our next is Liouville's theorem. So what is statement of Liouville's theorem? Why Liouville theorem came? Now the phase space density, that is rho, which is a function of qpt, is defined at any given point of time and it evolves with time. If we consider infinitesimal phase space volume, say d omega, which encloses several microstates of the system at time t, then each microstate evolves in time. Then how the phase space volume element d omega changes? This is represented by your Liouville's theorem, and the mathematical statement of Liouville's theorem is your d rho dash ps, that is your phase space density function del by del t of this one plus del, this is a Laplacian rho, that is density function into v is equal to 0. If v is constant, this part is 0, then del rho s by del t, you will find del rho ps by del t is equal to 0. This is called, this equation is called your Liouville's theorem. That is, in case of equilibrium, we will got it. So to derive this equation, Liouville's theorem is an important aspect, how the density function evolves under time. Then we can say, if we have 3n coordinate system, 3n q coordinates and 3n p coordinates, in time t, there are 6n dimensional phase space. So we have del d of qp. So we can write this one, that is del rho ps by del t dash, del rho dash ps by dt, that is differentiation with respect to time of the phase space density function is equal to d dt of this is del by del t of this plus summation I is 1 to 3n del rho dash ps by del qi into qi dot plus del rho dash ps by dpi into pi dot. So it indicates the Liouville's theorem deals with the representative points in phase space, and if we consider the rate at which the number of representative points change, if this is your phase space diagram and this is the volume, this is normal to the volume, the distance covered in this time is v into dt. So the representative points, if we represent in phase space, that will be del by del t integration upon omega rho dash ps qpt into d omega. So the rate at which the representative points flow out of omega across surface sigma is given as this omega d omega. In place of d omega, we have written that is v n cap ds. V n cap into d sigma. This represents small surface area. And v is the velocity vector, that is q dot t, p dot t. We have already told you that v is equal to q1 dot into q1 cap up to q3n cap, q3n dot, q3n cap, and p is equal to p, that is p1 dot into p1 cap up to p3n into p3n cap. Now we use Gauss divergence theorem. What is Gauss divergence theorem? That is a v n cap ds is equal to del a into dv. If we use this Gauss divergence theorem, then your final equation reduces to this one, that is del rho ps dash v is sum over summation I is 1 to 3n del by del qi rho dash ps q1 dot qi dot plus del by del pi rho dash ps pi dot. So if there is no source or sink in phase space, the rate of change of phase space density in the volume is equal to the net density flow. What is then mathematically we can write, that is del by del t integration rho d omega is minus del rho d omega. So this plus this one, that is del by del t rho dash ps qpt plus this one del of this is 0. Why this is possible? Because velocity and gradient vectors are defined in phase space by the volume element, and the volume element is an arbitrary number. So we can equate it, the integrand, we can equate the integrand to 0, and that is del rho dash ps by del t plus del rho dash ps v is equal to 0. If we consider this is equation of continuity, mark the in equation of continuity you have read del rho by del t plus del rho is equal to 0. This is equation of continuity. And if we consider the Hamilton's equation of motion, in classical mechanics we have Hamilton's equation of motion where the velocity q1 dot is represented as del h by del pi, and this is your del square h by del qi pi. Similarly, p1 dot is represented by minus del square h del qi pi. Therefore, if we put these two values here in the equation and equate it to 0, this equation reduces to del rho dash ps by del t plus this equation reduces to this form. This equation reduces to del rho dash ps by del t plus del rho dash ps by del qi into del h by del pi minus del rho dash ps by del pi into del h by del qi is equal to this factor, that is del rho dash ps by dt, which is also equal to 0. And what is this one? This represents the Poisson's bracket. Del rho dash by del q into del h by del pi minus del rho dash by del pi into del h by del qi. This is your Poisson's bracket represented here. Hence, d rho dash by dt is del rho dash by del t plus rho dash h, that is your Poisson's bracket. And the Poisson's bracket represents this equation, this equation 4.15. This is called your Liouville's theorem. What does it indicate? It indicates that the normalized phase space density function, that is rho ps, is though normalized, has dimensionless, it is also normalized as well as dimensionless. What are the consequences of Liouville's function? First consequence, when time evolves, that means time changes from t to t dash, then each of the microstate in the neighborhood of QTPT have small phase volume, and that is transported in such a way that the microstate changes relatively, and that is evolved the corresponding coordinate changes q t plus t dash and corresponding momentum changes p t plus t dash. So phase space volume remain unchanged. With evolution of time, Liouville's theorem tells the phase space volume remain unchanged. Similarly, the phase space density, which is represented in gamma space, and the element changes from qi to dqi and pi to dpi, the phase space volume, that is dw, it is the sum over continuous product dl qi into dpi. Here this is at a time t is equal to 0, and when it further time evolves, the phase space volume changes to a dash, b to b dash, and c to c dash. This is at a time 0, t0, and this is at a time t0 plus t. So what does it indicate? It indicates the trajectories which are drawn here, that is on evolution of time. And Liouville's theorem states that the conservative forces, that means, what do you mean by conservative force? Now, time dependent Hamiltonian, the phase space volume remain conserved. So what is statement of our Liouville's theorem? Now, for conservative forces, the phase space volume remains constant, or change in volume element can take place in time. The next conclusion is, a system in equilibrium, if a system is equilibrium, then del rho by del t is equal to 0. So if you go to Liouville's theorem, that is del rho by del t plus Poisson's bracket of rho h is equal to 0. When del rho by del t is equal to 0, hence for equilibrium systems, Poisson's bracket of rho h is equal to 0. What does it indicate? It indicates stationary ensembles is either constants or depends on coordinates qp or Hamiltonian qp. So this is how the time average and your the ensemble average, they differ and they are related with the phase space density. Now this gives rise to three ensembles. One is your canonical ensemble, microcanonical ensemble. Second one is canonical ensemble. The next one is grand canonical ensemble. So what is microcanonical ensemble? Microcanonical ensemble, that means if energy, volume, and number of particles remains constant, then we say the ensemble is a microcanonical ensemble. Suppose we have an isolated system in equilibrium. We have an isolated system that is in equilibrium, and the energy of the system is E. V is volume, fixed volume, and N is the number of molecules in fixed volume V. If E, V, and N remains constant for all cells, for a system of N particles, the total energy is fixed, and the number of particles and the volume is fixed in all these cells, then we say the system is in isolated equilibrium, and such an ensemble is called microcanonical ensemble. In a canonical ensemble, temperature, volume, and number of particles remain constant. T, V, N remains constant. In a grand canonical ensemble, our mu Vn, mu is your chemical potential, mu Vn remain constant. We will make a comparison on the last of this class, but first thing is, what is microcanonical ensemble? If E is energy, V is volume, N is number of particles, T is temperature, mu is chemical potential. If in all these cells E, V, N remains constant, then this is called microcanonical ensemble. If T, V, N remains constant, this is called canonical ensemble. If mu Vn remains constant, this is called grand canonical ensemble. So let us focus on microcanonical ensemble. In microcanonical ensemble, you have written here X represents your V and N, but EVN remains constant. Ex in all the cells, we have represented the equilibrium position of a microcanonical ensemble. And a microcanonical ensemble physically represents a group of systems which are in possible microstate called accessible microstates. The fundamental postulates of statistical mechanics tells the postulate of equal a priori probability for an isolated system, which indicates for a classical ideal gas of n number of particles in volume V is described by above condition, that is by equal a priori probability. It indicates that various possible microstates corresponding to given macrostate are distributed uniformly when system is in equilibrium. In other words, an isolated system in equilibrium is equally probable. That means in equilibrium, if we have an isolated system, then it has equal probability and they are accessible microstates. So let us consider a function, a probability density function, that is P, or microcanonical function will be defined as say rho MC. For microcanonical, we will say rho MC is constant. When rho MC is constant, when its Hamiltonian represent a fixed total energy. That is this one. Rho MC is constant when Hamiltonian represent a fixed energy. And rho MC is 0. Remember this equation. Rho MC is C constant when Hamiltonian is energy. And in otherwise case, this will be 0. So the constant is determined by using the normalization condition. What is that condition? 1 by omega 0. How can we determine the constant? By using this equation 1 by omega 0. All accessible states of omega, all accessible microcanonical states of omega, d omega into rho, MC means your microcanonical ensemble. That means 1 by omega 0 integration rho d omega is equal to 1. This is normalization condition for microcanonical ensemble. But we know rho MC is equal to C. Before this equation, we tell rho MC is equal to C constant. So this equation reduces to rho MC is taken out. That is C by omega 0, integration d omega is 1. Hence, the normalization constant C is omega 0 by integration d omega, which is omega 0. We know in gamma space, gamma is a function of energy and X represents for V and N, volume and a number of particles. This can be written as the thermodynamic probability 1 by omega, which is also a function of Ex. X corresponds to V and N. Hence, the thermodynamic probability function, we can express the density, microcanonical density, rho MC is reciprocal of Rho mc is reciprocal of thermodynamic probability density 1 upon omega, which is a function of Ex, x is Vn, into Dirac delta function, that is delta of h minus e. You know the property of Dirac delta function. So we can calculate the accessible phase space volume in microcanonical ensemble by using this equation. What does it indicate? It indicates that the density function of a microcanonical ensemble represents the total probability of various microstates. So considering that into account, we will apply it to calculate apply it to a classical ideal gas. What is classical ideal gas? Classical ideal gas means this is a non-interacting, non-relativistic gas. These are identical particles. Let that gas is a monoatomic gas, and each particle has mass m. It has fixed energy E. That means energy, we can say it varies between E minus delta E by 2 to E plus delta E by 2. Since this is a monoatomic gas and it is a microcanonical ensemble, E, V and N remains constant, then we will take an example by considering its trajectory. We will derive an expression. We can derive the expression for the entropy of the classical gas, and from which Sokor tetrode equation can be derived from it. So what do you mean by classical? Classical particle means the trajectory of each particle. Ideal gas, this is classical, non-interacting, non-relativistic. So classical means no internal degrees of freedom are assumed here. Non-interacting means the atoms have almost all energy in the form of kinetic energy, and momentarily the interaction energy can be neglected. Non-relativistic means we know the kinetic energy of a particle, epsilon I is equal to pi square by 2m. So the monoatomic state is represented by the that means it has no rotational and vibrational motion. So degrees of freedom is due to only translational motion of the particles. So if we consider the motion of the particle from minus infinity to plus infinity, then the phase space density function can be written in this manner. The phase space density function, that is rho mc. This is rho mc, that is microcanonical density function, is 1 upon omega, which is a function of EVN, because in microcanonical ensemble EVN remains constant and the variation of energy is possible with maximum up to delta E. And 1 by omega of this we have written, this is omega 0 by gamma of this one. So rho mc is 1 by omega, which is equal to small omega 0 by gamma space. And this is possible when the energy in the ergodic surface, which lies between E minus delta E by 2 to E plus delta E by 2, and the Hamiltonian lies between these energy states. One is E minus delta E by 2 if you have these two energy levels. One is E minus delta E by 2, other one is E plus delta E by 2. The Hamiltonian or total energy function lies there. Then rho mc is 1 by omega. Otherwise, it will be 0. What does it indicate? It indicates that for uniform distribution phase space density, the energy within this energy range or energy distribution, the distribution is valid, and we can analyze or we can compare this situation in terms of the original definition of our microcanonical density function by considering these ways. So what is first way? Now first write Hamiltonian of the system. So how can we consider the analyze or compare the situation? The first step is we have to write the Hamiltonian. We all know Hamiltonian is the sum of kinetic energy and potential energy. Here Hamiltonian is a function of QP. And for 3n coordinate system, this will be summation I is 1 to n Hamiltonian 1 to 3n degrees of freedom. For ith particle, the kinetic energy is pi square by 2m plus u. So m is the mass of the particle, u is the potential of the energy of the particle, and it is 0 inside volume V. And it is infinity outside the wall of the container. Remember, for a free particle, the potential energy is 0 within volume V, and outside volume V or at the walls of the container, the value of potential energy is infinity. So what will be our Hamiltonian for volume V for fixed energy? That will be Hamiltonian is h of QP, which is pi square by 2m, because u is equal to 0, and Hamiltonian represents the total energy of the system. So for n particle in 3n dimensional space, you can say this is p square by 2m is e, pi square is equal to 2me. That means p1x square plus p2x square up to p3n x square. Similarly, p1y square up to p3ny square plus p1z square up to p3nz square is 2me. Since we consider since we have considered the energy interval, that means Hamiltonian energy or total energy lies between E minus delta E by 2 to E plus delta E by 2. So we can represent the Hamiltonian in this manner, that is P square by 2m, which is equal to total energy E or fixed energy. This is our first work to define a Hamiltonian. So what is first step? We define a Hamiltonian, which is sum of T and potential energy U, or for a free particle, we suggested within a volume V, this is equal to 0. So Hamiltonian have this form, and the momentum is equal to 2me. So the second one is the number of accessible microstates. For this problem, how can we obtain number of accessible microstates? That means here E, V, N are constants, and the energy within the range of energy delta n. So the gamma function is represented the phase space volume gamma E, which is equal to energy E, volume V, number of particle n is equal to integration d3n q into d3n p. That means 3n generalized coordinates and 3n momentum coordinates. So the volume of the phase space is the integration of this one. But d3q is equal to our v, so d3nq can be represented as v to the power n, sum over continuous product all the n particles, this will be v to the power n. So what is phase space volume? Phase space volume will be now vn integration, this is all the momenta, that is integration d p d1 np d2 np so on d3 np, this is dv p, that Vn is the volume, that is volume generalized coordinate volume, and for momentum volume we have dvp 3n. This generalized volume dvp 3n is called hypervolume. Hypervolume of this space in momentum space. dvp 3n is hypervolume in momentum space, and we are able to calculate the volume in phase space and the hypervolume. Now to obtain the this ideal gas problem, we have to calculate what is value of this hypervolume. To calculate the value of this hypervolume, we consider a sphere. This is a sphere of radius r, and this radius r is equal to represent your momentum, that is equal to root 2 over 2me. So we say in three directions, that is P1 x axis, y axis and z axis, P1 x square plus P1 y square plus P1 z square is equal to 2me. That means we have told you total energy is 2me. Since energy varies from E minus delta E by 2 to E plus delta E by 2, so 2m E minus delta E by 2 is less than equal to your Hamiltonian or total energy of the system, that is this one, which is less than equal to 2m E plus delta E by 2. So this equation, the upper equation, that is P1 x square, P2 x square, this is the equation of a sphere in 3 dimension. This equation is a equation of sphere in 3 dimension. And the volume of the spherical shell you can calculate, that is our aim is to calculate the hypervolume. So we consider if this is the thickness, small thickness is your delta r is the radius, then the volume is calculated as dVp3 is equal to sp3. sp3 is your surface area of the hyperspace multiplied by this one, this is Tp. Tp represent the thickness of the shell. If we have a shell of radius r, this is a shell of radius r, and the thickness is your Tp, then the volume is your, that is hyperspace multiplied by Tp. So our aim is to calculate the hypervolume and the hyper surface area, and we calculate in momentum space the hyperspace surface area is equal to, if r is the radius, this is 4 pi r square, 4 pi r is your 2me, r square is 2me, that is, this is 8 pi m. Since this is a sphere, we know its volume is 4 by 3 pi r cube, so we obtain the volume, hypervolume can be putting the value of r, that is equal to 2me, we can calculate the hypervolume. And for spherical symmetry equation, we know this equation, that the angular coordinates in 3 dimensions are represented in 3 dimensions. The integration is 0 to pi, and theta is from 0 to pi, and in other direction the integration is phi is 0 to 2 pi. So this gives a factor 4 pi. And when you calculate the thickness will be, your thickness will be come across this factor. Thickness factor is this one, that is thickness Tp, thickness of this one is the thickness, this is radius, this thickness part, this comes around your 2me, root 2 over 2me delta E by 2. So we have calculated the surface area, we have calculated the thickness, hence we can calculate the volume. Surface area is your 8 pi me, and your thickness is your 2me into delta E by 2e. So 2e, this 80, this is 4 pi m into root 2 over 2me into delta E. This represents your hypervolume. Then when you calculate the hypervolume and we calculate the momentum space radius r is equal to root 2 over 2me, then we are able to write the total volume in of a spherical shell, that is dVpd, that is in d-dimensional momentum space, the volume, hypervolume is surface area multiplied by the thickness. Hence, we are able to calculate the hypervolume and hypersurface area. Similarly, you can calculate in k-dimensional space, you can calculate the hypervolume and hypersurface area. Now, the question is to derive the mixing entropy, that is Gibbs paradox. We have two systems, A and B. If we consider two systems and entropy of the system, entropy of one system is A, say that is SA, entropy of other system is say SB. Then you can say if you mix the two systems, then entropy SA, yes, total entropy S is equal to sum of the two entropy SA plus SB. But Gibbs paradox resolves, no, S is not equal to SA plus SB. When entropy of two, we mix two systems, or the partition between two systems having number of particles say Na, volume is Va, and energy is Ea. In second B system, this is Nb, Vb, and Eb. The mass is Ma and Mb. When you mix the gases, you will find S is equal to SA plus SB plus another factor, that is 2 NKB log 2. Log 2. This additional factor arises due to interaction, which was later proved by quantum mechanics, later solved by this Gibbs paradox is solved by quantum mechanics. We know entropy is additive in nature. If we have two systems, two gases, which mix ideal gases, they mix each other, then entropy should be S is equal to SA plus SB. But instead of that, SAB is equal to SA plus SB plus 2, another factor 2NK log 2 arises. And quantum mechanics suggested the parameter that when they mix each other, then their volume becomes 2V, number of particles become 2N. As a result, they are indistinguishable, for which they have proved S is equal to SA plus SB. So while deriving this equation, we know the entropy. We make a simple transformation. We consider a classical gases, the classical ideal gas. Ideal mean not only ideal but non-interacting, non-relativistic classical gas. So we know entropy is an extensive parameter, and the energy E is changed to, is scaled by, E changes to lambda E, V is replaced by lambda V, where lambda is a scale parameter, N changes to lambda E. Please go through the expression of entropy. Entropy of first one, that is a system, S dash is a function of energy, volume, and number of particles. And by scaling factor, this is lambda E, lambda V, lambda N, which is for a ideal gas, that is lambda times NKV. We have scaled here. Initially it was NK beta. K beta is Boltzmann's constant. N is your number of particles into 3 by 2 plus log of lambda V by HQ. Yesterday we have derived this expression while deriving Maxwell-Boltzmann equation. That is 4 pi m lambda E by 3 lambda N, this factor. And the entropy in other system, this can be represented as lambda, which this is your S plus NK beta lambda N log of lambda. Here S is not an extensive quantity because there is a Gibbs paradox, for which S is not equal to S1 plus S2 plus S dash plus S2. So if before mixing of two gases, you can find one gas have number of particles N1, V1, T, temperature, and P. Second gas has number of N2, V2, T, and P. After mixing, remember the number of particles is N1, N2, but volume becomes V1 plus V2, temperature, pressure remains same. So if you look into this picture, this is before mixing. These are two ideal gas systems. This is a system after mixing. So what you will find, since the temperature is same in two sides, you can find the temperature in this system. This is T, and here temperature is T. So the first law of thermodynamics expression for entropy indicates the energy each one, E1 by N1, must be equal to E2 by N2, and equal to E1 plus E2 by N1 plus N2. Then, since pressure is the same, you can also write from this classical ideal gas equation PV is NKT, NK beta T, and this indicates N1 by V1 is equal to N2 by V2 is N1 plus N2 by V1 plus V2. Hence, we can write the expression for entropy as STVN, S which is entropy, which is a function of temperature, volume and number of particles, is Nk beta log V plus Nk beta sigma. What is sigma? Sigma is represented as that function. This is represented, this entropy expression you can find. If you put that, this will be 2 pi k beta T. 2 pi mk beta T to the power 3 by 2 by HQ plus 3 by 2. So you find the sigma is a function of mass. This is function of mass of the gas. Not only it is a function of mass, k beta is a constant, 2 pi is a constant, HQ is your volume of phase space, and this T, this is a function of mass and temperature. Hence, we can say the total energy is 3 by 2 NKT. You have derived in case of your equipartition theorem that for 1 degree of freedom, energy is half NKT, and here total energy is 3 by 2 NKT. So, we consider these two cases of gases, and when you consider two cases of gases, there are various problems. The gases are separate on two sides, or gases are same on two sides. Case 1 we will consider the gases which are different on two sides, their masses are different. M1 is not equal to M2. Let before mixing, the entropy of the systems are S1 and S2. So what will be their equation? Their equation is S1 plus S2. Their equation is like this, that S1 is equal to N1 K beta log V1 plus N1 K beta sigma 1. S2 is T V2 N2, which is N2 K beta log V2 plus N2 K beta sigma 2. When you mix these two, since before mixing, the sensitivity was entropy was initially an extensive quantity, you add these two, you got this equation. But simultaneously, I have told you, you will obtain an additional factor that comes across this delta S, the entropy mixing delta S at temperature T. The difference is final entropy minus initial entropy. So what is this one? Delta S T difference come across S final entropy minus initial entropy, that is N1 K beta log. I have told you the volume increases V1 plus V2 by V1 plus N2 K beta V1 plus V2 by V2. Similarly, the particle density is same on both sides. We can write delta S T difference, that is change in entropy, is instead of this one, this is log of V1 plus V2 by V1. We have replaced N1 plus N2 by N1, and V1 plus V2 by V2 is replaced by N1 plus N2 by N2. So we find Gibbs paradox arises when we have same gases on two sides and we allow these gases to mix each other. And we find the entropy mixing will be zero at constant temperature and pressure. When gases are same on two sides, that means their masses are same. You allow those same particles in the similar manner, then what you will obtain? You will obtain this expression delta T for same mass, that is different mass, is N1 K beta log N1 plus N2 by N1 plus N2 K beta log by this one. N1 plus N2 is obviously greater than N1 or N2. So this indicates the paradoxical result where two identical gases at same temperature and pressure are allowed to mix. By removing the partition, they undergoes a reversible process, and the contradiction, that is known as Gibbs paradox is resolved by considering for a large n, when the gases mix each other, we have two volume V and V1 and V2 becomes 2V, N1 and N2 becomes 2N. As a result, we obtain SAB is equal to SA plus SB. And in that case, we suggest that entropy obeys the additive property by considering the quantum correction. In this case, that is your microstate. In this micro canonical ensemble condition, the entropy is a limiting case of, or thermodynamic limiting case, when n tends to infinity. When n tends to infinity, that is the corrected thermodynamic probability function E omega EVN is omega EVN by n factorial, which is V to the power n h to the power 3n by n factorial into 2 pi me 3n by 2 by 3n by 2 factorial into delta E by E into 3n by 2. So what we find? We find the this Gibbs paradox can be resolved when if we consider the quantum mechanical aspect. And from the corrected thermodynamic probability function, we calculate the corrected entropy function, or modified entropy function in the limit of thermodynamics, that is S corrected, S means entropy, corrected entropy, nk beta 5 by 2 log V by NHQ 4 pi me by 3n to the power 3 by 2. This is called Sokor-Tetrode equation or correct fundamental equation. So what does it indicate? This Sokor-Tetrode equation indicates when the entropy is the same, that is equal to 0, change in entropy delta S is equal to 0, and we have again two cases. The initial and final entropy of the two states can be represented as follows. That is, if gases are on two sides are equal, different mass, and gases on two sides have same mass. So before partition, in the similar manner, we can write S1 is equal to N1 k beta log V1 by N1 plus log k beta tau 1. And S2 is equal to similarly N2 k beta log V2 by N2 plus N k beta tau 2. These two equations. S1 is equal to T V1 N1 N1 k beta log V1 by N1 plus N1 k beta tau 1. S2 is equal to N2 k beta log this one. So what is total entropy? Total entropy is the sum of S1 initial state plus S2 initial state. If you add these two, you will obtain these four terms. This plus this, these four terms. So after partition is removed, the insulated portion has a volume becomes V1 plus V2, but temperature remain constant. So total entropy of the system after mixing, when we have different gases, gives the same result. That is delta S T difference is final entropy minus initial entropy. That is N1 k beta log V1 plus V2 by V1 plus N2 k beta log V1 plus V2 by V2. Same thing. And in terms of number of particles, only replaced V1 plus V2 by V1 is replaced by N1 plus N2 by N1 in these two equations. So we find the entropy mixing of the reversible process is greater than 0 as we have expected, which gives birth of your Gibbs paradox. But in case of reversible process, when the gases are same on two sides, so similarly, for you add these two terms S1 and S2, which are represented as N1 k beta log V1 by N1 plus N1 k beta T plus N2 k beta V2 by N2 plus this one, you will find the addition of these two gives rise to a factor that is 0. That means the correct expression for entropy delta T when we have same gases is equal to 0, and it represents that the entropy is an extensive parameter. This resolves the Gibbs paradox. So what is the conclusion? Gibbs suggested S being an extensive parameter, S should be S1 plus S2, but there is a factor of 2nk log 2 which arises due to classical physics. But when we say this quantum physics and we assume that the molecule of each system are indistinguishable, the volume V becomes V1 plus V2, say 2V, and a number of particles becomes 2n, as a result of which we resolve this paradox and we prove 2S is equal to your SA plus SB. Then arises entropy of two energy level systems. If two energy level systems, that means if we have n distinguishable and non-interacting atoms which are trapped in a solid, then they occupy two non-degenerate single particle energy states. Say N0 is number of trapped atoms in the ground state, and N1 is number of trapped atoms in the excited state. And they have an energy that is E. So N0 number of molecules have 0 energy, or atoms have 0 energy. N1 atoms have epsilon energy. Hence we can write total number of atoms, that is N is equal to N0 plus N1. And the total energy is 0 into N0, means 0 energy is possessed by N0 atoms, epsilon energy is possessed by N1 atoms. So total N1 is equal to E by epsilon 0. Since we are dealing with the discrete energy system, we need not calculate the phase space volume. So the number of distinct ways in which n distinguishable particles can arrange themselves is by this relation we know earlier, that is omega, which is a function of En, is n factorial by n1 factorial into n minus n1 factorial. That is combination of n1. So this is your equation of binomial coefficient. And by division of these factorials, we suggest that the configuration, we can interchange those configuration. Hence, when two energy systems mix each other, the expression for entropy becomes S, which is a function of energy and number of particles, can be written as K log omega, K beta log, instead of omega, we have used this one, that is n1 by n factorial by n1 factorial into n minus n factorial. So by using Stirling's approximation, we obtain this expression, and taking some corrections, we obtain the expression for the total energy as n epsilon into E exponential of by n epsilon divided by e to the power epsilon by k beta t plus 1. This is the expression for total energy due to two energy level system mixing. And if you have a curve for two level system, this is the curve. This is total n epsilon energy, total energy, and this represents your negative temperature. That means when we have a peak of energy, the energy increases, you will find there is a decrease in temperature. The energy increases, but the temperature decreases. So this is one curve, this is the other curve. When we have increase in energy, E by epsilon n, after peak, this temperature gradually decreases. So this indicates that we have the negative temperature exists. That means we know the expression of temperature, that is 1 by T is del S by del E. The negative temperature and the positive temperature, when brought in thermal contact, the energy will flow from a positive negative temperature end to positive end or negative state to positive state. So according to
Hello.
concept of temperature, according to hello,
Hello.
huh,
Sir, good
please tell.
evening.
Good evening. Good
Sir,
evening.
it is a kind request from my friends and also from me that can we get any notes, important notes from this unit and from any blogs?
Yes, 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 yes. I'll share. Okay, I'll share. Okay, I'll share.
Okay, sir. Okay, sir. Sir, can I
Okay,
have your
okay.
number, please?
Yeah, 6370
Yes,
979755. 6370
9797
double five.
double five.
Okay.
Sir, and your name?
Dr. Prabhat Ranjan Lenka.
Okay, sir. Sir, we are like 505 students in a group, and
Hmm.
in the first year classes, we also requested our lecturers to share the notes, like particular notes important for our MSPH classes, and they also share their notes, which are very much helpful during our exam time. And I hope
Hmm.
that you also share the these notes, and that will be benefited for
Statistical
all of us.
physics notes. Okay, okay.
Okay, thank you,
Then,
sir.
then what is the consequence of negative temperature? Then it indicates the system must be in thermal equilibrium. It has finite upper and lower limits. It must have negative temperature states which are separated from the positive temperature states. Then what we find for an classical ideal gas, where we have distinct microstates, there are six n coordinate systems. We have to integrate over all possible accessible phase spaces which are consistent with fixed energy. And for two level problem with distinct microstates, we have to calculate the number of microstates directly by using the binomial expansion. So this is all about our microcanonical ensemble. Then we'll proceed to canonical ensemble. Then in canonical ensemble, what happens? The temperature, volume, and the number of particles remains constant. Temperature remain constant, volume remain constant, and the number of particles remain constant. Here we will discuss the canonical ensemble along with the ideal gas system for canonical ensemble and the relative fluctuation of energy. We will discuss the virial and equipartition energy theorems. As I have told, in case of canonical ensemble, we have this fixture that is temperature. This x corresponds to V and N, that is volume and number of particles. TVN remains constant. We consider two systems, S1 and S2, which are separated or insulated and impenetrable or immovable rigid partition, separated by such type of partition which are insulated, impenetrable, and immovable rigid partition. Let's have two systems characterized by two microstates, that is omega 1, which is a function of E1, V1, N1, and omega 2, which is a function of E2, V2, N2. So when you describe such type of microstates, what is the Hamiltonian? The Hamiltonian, the total Hamiltonian H0 is individual Hamiltonian of system 1, that is HS1, plus Hamiltonian of the system HS2, plus that is integrating Hamiltonian or interaction Hamiltonian, or you say this interaction Hamiltonian is due to your thermal exchange. So total Hamiltonian H0 is the Hamiltonian of system 1 plus Hamiltonian of system 2 plus H interaction. But if it is weakly interacting system, H interaction is 0. H0 will be HS1 plus HS2. But when you have assembly of isolated systems, at that time the H0 is represented by S1 plus S2 minus this interacting term is a fixed energy, that is E0. What is E0? E0 is E1 plus E2, and that due to that is called the significant interaction energy. And in this case, the particular microstate is given by, that is rho, the density function rho is 1 by, that is omega 0 E1 E2 into, this is delta of your Hamiltonian function, delta of the Hamiltonian, that is delta of HS1 plus HS2 minus E0. So this probability function which arises, which gives rise to your density function, gives the number of microstates for a closed system exchanges thermal energy to its companions. That means for that reason, the temperature, volume, and the number of particles of the system remains constant here. In case of your canonical ensemble, you will come across certain equations which indicates that two systems can be in thermal equilibrium, provided we consider that is for thermal equilibrium we must have 1 by beta T, that is if S is entropy, ds by dE, that is change in entropy when a number of particles and volume remain constant, divided by dln thermodynamic probability function of energy by dE is 1 by beta T, which is constant. So it can be mentioned that these two conditions indicates that beta, which is equal to 1 by k beta T. K beta is Boltzmann's constant, that is 1.38 into 10 to the power 23. If this equation is obeyed, then thermal equilibrium is possible in a canonical ensemble. And we know the expression for entropy yesterday, S is equal to K ln omega. Entropy is equal to K ln omega, statistical definition of energy. This indicates that in a canonical ensemble, what happens? Now, it follows the first law of thermodynamics. It explains the zeroth law of thermodynamics. It is also able to explain the second law and third law of thermodynamics. Let us consider the expansion of such type of functions. We consider certain amount of gas, its volume change, and it is especially a reversible volume. Let the change in volume is delta V. So whenever there is a change in volume, we know from first law of thermodynamics there is some work done delta W. Whenever there is some change in work delta W, we can write the change in entropy also. Entropy we know delta S, change in entropy you can measure, and S is a function of initial energy E minus your change in, that is P delta V, change in entropy, P is your pressure, and volume changes to V plus delta V. So initial state of a system is S EV, initial entropy is a function of energy and volume. When internal energy is added, the energy becomes E minus P delta V and volume becomes V plus delta V. So we can write the change in entropy delta S according by S is a function of E minus P delta V. This is according to first law of thermodynamics plus and V plus delta V minus S of EV. You expand it by Taylor's expansion. By Taylor's expansion, you obtain this is S of EV minus del S by del E P delta V plus del S by del V delta V minus S of EV. Hence, you obtain this is del S by del EV into P delta V plus del S by del VE into delta V. So, what we obtain? The entropy tends to attain maximum value, then the variation of entropy goes to 0. When entropy attains maximum value, the variation of entropy becomes equal to 0, and it satisfies the first law of thermodynamics equation, that is ds is equal to del E by del T, plus P by T into dV, or D is TdS minus PdV, which is also called TdS equation. Similarly, the second law of thermodynamics, that is transfer of cold body to hot body temperature, the entropy becomes increases when they attend the change in entropy after the system attains equilibrium is given by this one. In first case, the energy is E1. In second system, this is E2. So change in entropy is S1 E1 average minus S2 E2 average minus sum of these two, which is greater than 0. So this second law of thermodynamics indicates that the thermal contact not lead to any change in entropy. It corresponds to a reversible process. Now we come across the third law of thermodynamics. What is entropy and third law of thermodynamics you have read? This indicates when temperature at absolute zero temperature, the entropy goes to zero. If there exists one unique accessible configuration state for which omega is equal to 0, the third law of thermodynamics suggests S is equal to K ln K beta T when T is equal to 0. The theoretical basis, third law of thermodynamics, indicates there is a statistical approach. And the statistical treatment provides a natural basis for phenomenological or thermodynamical law. And we know in this case also we can derive the chemical and mechanical equilibrium. What is the condition for that one? If we recall two systems and its thermodynamic probability is two systems having volume V1 and V2 and energy E1 and E2, then we can say d by dE of log omega 1, which is a function of E1 V1, must be equal to of the second system d by d log omega 2 E2 V2 by d. So d log omega 1 E1 V1 by d V1 is d log omega 2 by d V2 EV2. This condition of equilibrium allows us to define thermodynamic parameter eta, and this indicates what is thermodynamic parameter. This eta is d log omega by dV. That is, equilibrium is defined by two parameters. One is beta, another is eta. So the equilibrium of a system due to exchange of particles can take place. Suppose if n1 number of particles in the first system, n2 number of particles in the second system, and there is a exchange of energy, then we say these parameters beta and another parameter we have defined eta is d log. These two parameters define the quantity, and by joining this, mixing this, we can define a third parameter, that is zeta is equal to d log omega by dn, which is a function of VE and average number of particles. This represents the equilibrium system. So these microscopic parameters we have defined. In first law of thermodynamics, we have obtained d is TdS minus PdV. We can add another quantity, that is mu. Mu is your chemical potential multiplied by dN. When you consider this mu, what will be dE? dE will be your TdS minus PdV plus mu dN. As a result, ds is dE by T plus P by T into dV minus mu by T into dN. So we define that parameter eta, the pressure by temperature, comes across K beta times eta. P by T is eta, or eta is defined by P by K beta T. This is a very small equation, but it has great implications. Since zeta is the combination of eta and beta, P is pressure and mu is chemical potential. So on the microscopic basis, the thermal and chemical and mechanical equilibrium is satisfied if to this condition is obeyed. That is, zeta is minus mu by K beta T. Mu is chemical potential, K beta is Boltzmann's constant, T is temperature, and eta is P by K beta T. Here, the next question is, what is the probability of these microstates in a canonical ensemble? and what is the expression for canonical partition function. So in order to consider an ensemble of these systems in equilibrium, having same temperature, same number of particles and same volume, then we consider the thermal contact of two systems or a system with a reservoir, either two systems or a system with a reservoir. This will be better. So the system, if S is the system, R is the reservoir, then naturally the number of particles in the system is much less than number of particles of the reservoir. First assumption. Second one, the composite system and the reservoir, the system and the reservoir forms a composite system. That means S plus R is isolated and the total energy is fixed, that is E0. And the reservoir is sufficiently large so that its temperature does not change due to interaction of the system. It is so large, if a system enters into a reservoir, there is not absolute change, not so much change. And the fourth assumption is the boundary of the system and the reservoir is impenetrable, rigid, so number of species and volume of the system are fixed. The interaction between the system and the reservoir is weak so that total Hamiltonian of the composite system can be written as, I have told you total Hamiltonian H0 is here Hs, Hamiltonian of the system plus Hamiltonian of the reservoir. So energy of the system, total energy, is the sum of Es plus Er. Since the reservoir is considered large compared to the system S, so Es by E0 is equal to 1 minus Er by E0, which is much less than 1. So we can find its probability. When we calculate its probability, we will find we can correlate it with a partition function. That's why the probability is written as here, that is rho k, say Ek is the energy corresponding to kth microstate, and for a composite system the probability density is represented as omega 0, which is a function of energy Ek and E0 minus Ek. E0 is the total energy and kth state has energy, kth microstate has energy Ek. So rho k, that is density, is directly proportional to rho 0, which is a function, omega 0, which is a function of Ek, E0 minus Ek. So rho k can be written as C. C is the proportionality constant here. So rho k is equal to 1, and the probability of the system can be represented by this equation in the expansion, Lorentz expansion, as log omega r. That means for a reservoir with kth state, this is ln omega r with maximum energy E0 plus ERK minus E0 into del log omega r by del E. So here we can neglect the higher terms and we obtain the equation, that is omega ER. If you neglect, and we will obtain a log omega r, EKR is log omega r E0 minus EK by K beta T. Higher terms are neglected. So we obtain the density function rho k, which is C times C omega r times E0 minus EK, or which is equal to C prime e to the power minus epsilon by kt. Hence, we obtain the density function after some mathematical simplifications. We obtain the density function rho k as Ek by K beta T divided by Z, which is a function of T and Vn. X is Vn. What is this Z? This Z is called canonical partition function. This canonical partition function Z Tx is e to the power minus beta Ek. This is canonical partition function, and it is already sum over for k independent states, microstates, k independent states. So Z is called your partition function for canonical ensemble. And there are some alternate expressions for canonical function, and the alternate expression, the same thing you will obtain, that Z is equal to e to the power minus epsilon by k beta t into omega, which is omega s, that is for system, omega s, which is a function of energy. The same thing you will obtain, that is your canonical partition function. And we know the density of a function. If we consider some discrete variables, the density function rho, which is a function, probability density function, which is a function of energy, then we can choose a random canonical ensemble whose energy varies from E to E plus delta E. Then rho ED can written as GE exponential minus E by k beta t into d divided by integration 0 to infinity dE GE exponential minus E by k beta t, which is GE e to the power minus E by k beta t by Z into d. So you can find this term represent your Z. This is your Z, that is represents the partition function for canonical ensemble. The partition function for canonical ensemble Z, which is a function of Tx, can be written as integration 0 to infinity d G e to the power minus epsilon by kt. Remember, this is your density function, rho e dE within an energy range dE e to E plus dE is G e to the power minus epsilon by kt d divided by Z. What is Z? This Z represents Z, which is a function of Tx. Tx stands for V and N, volume and number of particles, is integration 0 to t dE, this denominator part. This is your canonical partition function, and the total your probability density within energy E and E plus d by E with a variation of d is equal to GED, which is the number of energy levels in the interval. So the partition function Z, the canonical partition function ZT in an ensemble can be expressed in a Laplace transform of the density function G. If we consider G is another density function, then we express this in terms of the Laplace transform of G is your partition function. You see, this is ZT is dE GE e to the power this. If you consider the Laplace function of GE, then you are able to obtain the canonical partition function. And what happens? And in conversely, the density of a state can be obtained by considering the inverse Laplace transformation. So, when you consider the Laplace transformation of the density state function G, you are obtaining the partition function. When you are taking the inverse Laplace transformation of the partition function, you are obtaining the density function. So this indicates the transform of a partition function, the density states G increases with increase in energy, because there is a factor e to the power minus E by k beta t. So you can find the density state Ge increases. When E increases, Ge increases. And e to the power minus E by k beta t, it indicates when energy increases, e to the power of this function decreases exponentially, and rho E can be, which is the product of G into e to the power minus epsilon by k beta t, initially increases, then attains maximum value and then decreases. This maximum value is the most probable value of energy. You can see this is the GE Laplace transformation of a partition function. When GE increases a maximum value, then rapidly decreases, and the factor responsible for the rapid decrease is e to the power minus beta e. This is within the range, this is the range, this is the factor GE and e to the power minus beta e. So probability of rho e is the product of two functions GE, which increases with increase. As energy increases, this increases, and it decreases with increase in E. Increases, then decreases with increase. This is called negative temperature region and the most probable value of the energy state. But in classical physics, we have phase space. We define phase space as the density in terms of density function rho qp, and in Hamiltonian is represented by qp. Then we can express them in state of in these number states, that is GED, which expresses the partition function. How? Now we can express the partition function ZTX is 0 to infinity dE double integration d omega by omega 0 delta of h minus e to the power minus e by k beta. This is a Dirac delta function. When h is equal to e, you know this has a fixed energy, and d omega represent your phase space function. So the canonical partition function can be represented as the product of two, and corresponding the your thermal density, thermal probability can be represented as GED, that is d omega by omega 0, that is Dirac delta function, delta of h minus e into d. For indistinguishable particles, if we express it in terms of integration, then z, the partition function, changes to d omega by omega 0 d delta of h minus e from delta function of h minus e into e to the power minus e by kt, where the Dirac delta function can be, which expresses the canonical partition function. When this value is put here, you obtain z of tx is equal to d omega by omega 0 e to the power minus h by k beta t, which is 1 by h to the power 3n d to 3n q d 3n p. This is phase space volume multiplied by e to the power minus beta qp. Hence, ZTVN for indistinguishable particles, this is the value of canonical partition function. Z is 1 by n factorial h to the power 3n d3n q d3n p e to the power minus beta h. This is your canonical partition function, and the probability density function rho qp is e to the power minus h by k beta t divided by double integration of d omega by omega 0 e to the power minus h by k beta t. But in several cases, we can represent this probability function in terms of our Hamiltonian, which is a function of coordinate and momentum. If you consider a large number of several particles, then Hamiltonian HQP can be written as small hi. I means Hamiltonian for ith particle, which is a function of qi and pi. So z, which is a function of tvn, can be represented 1 by n factorial h to the power 3n d3n q d3n p e to the power minus beta h. And finally, you got the expression. This is the expression of your partition function, that is 1 by n factorial 1 by h3n d3n q d3n p e to the power minus beta summation I is 1 to n hi qi pi. In this manner, you can take first particle 1, 2, 3 and so on. For n times multiplication gives rise to our partition function. This is canonical partition function. And the canonical partition function can be also represented in this term, introducing the part, this n is equal to 1, you have 1 by n factorial 1 by hq d 3qp d3q dqp e to the power minus beta h for a single particle. If n is equal to 1, this reduces to 1 by hq d3q d3p e to the power minus beta h. So ZTVn can be written as ZTV1 to the power n divided by n factorial. This is the relation for canonical partition function. And this is true for indistinguishable particles. Z is equal to Z1 into Z2 into Z3 divided by n factorial. For distinguishable particles, remember, for indistinguishable particles, Z is Z1 into Z2 into Z3 by n factorial. For distinguishable particles, Z, canonical partition function, is Z1 into Z2 into Z3. So the individual partition functions, we can express the phase space density in terms of partition function. The expression for phase space density rho, which is minus e to the power minus beta h by z, that is n factorial e to the power minus beta h by z into e to the power minus beta h by z. So the phase space density is expressed by rho is equal to e to the power minus beta h divided by z. Now, there is a relation exists between thermodynamics and statistics for canonical ensemble. In thermodynamics, we know Helmholtz free energy function. Helmholtz free energy function F is a function of temperature, volume, and number of coordinates, or Vn you can x. F is a function of Tx, which is equal to minus k beta T log z. Log z is your statistical partition function. F is your Helmholtz free energy function, that is F is equal to minus k beta T. So we can represent this, and we know there exists a close relationship between statistical partition function as well as our Hamiltonian, our thermodynamics, that is Helmholtz free energy function. Next heading is ideal gas in canonical ensemble. As we have considered in microcanonical ensemble, similarly we can proceed in canonical ensemble. So the first step, if we consider a classical ideal gas having temperature T, volume V, and number of particles N, TVN, then write its Hamiltonian. The first point is write Hamiltonian. Hamiltonian is K. HQP is KQP plus UQP, and K is your Pi square by 2m, that is your kinetic energy. This is first step. And similarly, UQP is infinity outside the volume and 0 inside the volume in that case. Then write its partition function. Second step is write partition function. What is partition function? Z, write this equation. Z is a function of temperature, volume, number of particles. That is 1 by n factorial into h to the power 3n integration sum over continuous product over I particles d omega I into e to the power minus beta h. But we know the phase space volume, the sum over continuous volume d omega I is d3n qi into d3n pi. So our final partition function, by mathematical analysis we obtain that this ZTVn is v to the power n by n factorial into lambda to the power 3n. So in thermodynamics of an ideal gas, this is your statistical partition function. In thermodynamics, we know the Helmholtz free energy function F is equal to minus k beta T log Z, or minus k beta T. What is Z? Z is your v to the power n by n factorial 2 pi m k beta T by h square to the power 3n by 2. So by using Stirling's relation, we can rewrite the above equation, and we obtain the same equation that is obtained in thermodynamics. P is equal to minus del F by del V, and S is equal to your Sokor-Tetrode equation that is minus del F by del T gives you this sucker tetrad equation, that is S is equal to n k beta 5 by 2 log V by 2 pi m k beta T by H square. And the expression for chemical potential mu becomes del F by del N. You find when you find del F by del T, pressure is minus del F by del V, entropy is minus del F by del T, and chemical potential is del F by del N, and the expressions, this is n k beta T 5 by 2 log V by N 2 pi m k beta T by H square to the power 3 by 2, and this factor is not there, so you get this is the chemical potential, this term. Hence you write this total energy is F plus Ts, which is equal to 3 by 2 n k beta T. So entropy is expressed as EVN, that is equal to n k beta 5 by 2 log V by N 4 pi m, this is the average energy by 3 h square n to the power 3 by 2. This is same as microcanonical ensemble. If you replace the fixed energy microcanonical ensemble by average energy of canonical ensemble. So a question asks, in which condition the microcanonical ensemble becomes canonical ensemble? The entropy of microcanonical ensemble and canonical ensembles are possible, are replaceable, provided the energy is replaced by the average energy. And we know there is a relativistic fluctuations of energy due to this partition function, and this is due to relativity fluctuations we derive the expression for specific heat. And this gives us a relation, a connection between microcanonical ensemble as well as canonical ensemble. Which equation gives this result? Now, this is given by the factor. Yesterday you have read a factor, that is sigma square, the variance factor. If you consider the variance factor, you can have a relation between kinetic energy, a canonical ensemble and microcanonical ensemble. Next, we have some focus on virial and equipartition theorem. Virial theorems. What are virial theorems? If we consider the average value of any quantity xi del h by del k in classical phase space, and our Hamiltonian is h, then average of this one, that is xi del h by del xk, is integration of omega xi del h by del xk into d omega by d omega. What is d omega? Is the phase space volume. If you start from this one, you will come across a situation where the just 1 minute. You will come across a situation where the average of xi del h by del xk, this gives rise to the to specific heat condition, that is xi del h by del xk becomes equal to delta ik k beta t. And in two specific cases, if you consider xi is equal to xk, then this is equal to average momentum. In xi state, we take pi momentum average. This is 3 nk beta t. If you take a coordinate space, then this will be only k beta t. So these two cases suggest that the Hamiltonian of the system depends quadratically on the generalized coordinates as well as momenta, which is nothing but your virial theorem, and from this we obtain the for a Hamiltonian average energy or Hamiltonian energy average for 6n degrees of freedom is 3n k beta t, and in general the total quadratic degrees of freedom of the Hamiltonian is dk beta t by 2. So the degrees of freedom, each degree of freedom is associated with an energy half k beta t, that is your law of equipartition of energy. When you consider our next step is a grand canonical ensemble. When you consider the grand canonical ensemble, you will find the mu, V and L, they remains constant. In that case, you will find the mu is the chemical potential. So we have to find here the probability function. The probability function, the same case here, T mu, temperature mu and X, T mu and X remain same. So you calculate the total energy, which is the function of system as well as reservoir. Total energy E0, maximum energy, sum of your system energy plus reservoir energy. Total number of particles is the number of particles of the system plus number of particles of the reservoir. You start with that concept, then you will obtain these two equations. That is ES by E0 is 1 minus ER by E0, which is much less than 1. Similarly, number of particles NS by N0 is 1 minus NR by N0. And this indicates that we have a density function that is rho, which is the function of Kj, which is function of Nj, is equal to e to the power minus mu beta n plus mu beta n into partition function z tvn divided by L, where z tvn is canonical partition function and L tv mu is your grand canonical partition function. That means canonical partition function and grand canonical function altogether gives rise to the density of a function, and density of phase space density according to grand canonical phase space density rho gc is e to the power minus beta h by L, where L is grand canonical partition function. And for distinguishable particles, this is L TV mu is represented as 1 by h to the power 3n integration over phase coordinates, phase space, that is double integration, coordinate d3nq and d3np into e to the power minus beta h. Plus there is an additional factor mu bn. This mu is your chemical potential, which is responsible for your grand canonical partition function. So L T mu x, L T mu v represent the expression for n distinguishable particles. And the ensemble average physical quantity O can be written as ensemble average is sum over K, sum over J, O Kj into rho Kj. Kj represent two states of this function. Hence, grand canonical partition function and canonical partition functions can be correlated, and they are exactly relation with thermodynamics. The same relation we have seen in thermodynamics. We know an equation that entropy S is related with temperature. In the same thing, we obtain the entropy S is related here, that is Ts is equal to E average energy minus chemical potential times total number of particles plus K beta T into log L. L is your grand canonical partition function. And this gives the thermodynamic relation, that is d phi. Phi is your grand canonical potential by grand potential, which is expressed in terms of thermodynamics as minus S dt minus P dV minus average of number of particles into d mu. D mu is change in chemical potential. So we can represent this grand canonical. There is a close relationship between thermodynamics and grand canonical ensemble. The grand canonical partition function L can be written there in terms of the variables or parameters of thermodynamics. Now we can have a comparison between three types of statistics. First one, microcanonical ensemble, canonical ensemble, grand canonical ensemble. What are the parameters? In a microcanonical ensemble, NVE remains same. In canonical, NVT remains same. In the grand canonical, mu Vt remains same. Mu is chemical potential. What is the fundamental function? Number of accessible microstate is omega is equal to sum over this summation over m1, or this is delta function of H minus E. Here it is partition function z is equal to e to the power minus beta I. Here it is Grant partition function L is equal to e to the power minus beta I plus beta mu. And the probability of microstate is in microcanonical ensemble rho m is 1 by omega. In canonical ensemble rho m is e to the power minus beta I by z. In grand canonical ensemble it is e to the power minus beta I plus beta mu m by L. So the thermodynamic potential entropy S is k beta log omega, and the change in entropy is d by t plus p by t dv minus mu by t dn. In canonical ensemble, free energy is minus k beta t log z, or F is average energy minus Tf, and dF is minus SDT minus PdV plus mu dn. Similarly, grand canonical ensemble, the grand potential phi is minus k beta TL. Only you find here all the thing here omega, z, and L are equivalent quantities. Here this is E minus Ts, but additional factor is mu into average of n. Here also mu dn, but mu is replaced by your n d mu. This is the only change in the grand potential and free energy of canonical functions. So these are the expressions for today, and any questions from your side? Okay, thank you for your patience. Let us